Hey, welcome back to you guys, your favorite trig course. We're going to take a look at right triangle trig today in applications. If you remember from last time, we talked about the SOHCAHTOA, right? Sine is opposite over hypotenuse. The way I was taught it was, oh heck, another hour of algebra. That's how I was taught SOHCAHTOA. But anyways, we got the sine is the opposite side over the hypotenuse. Cosine is adjacent over hypotenuse. Tangent's opposite over adjacent. And of course, they're reciprocals, right? Cosecant flips the sine over. Secant flips the cosine over, and cotangent flips the tangent over, right? So let's go ahead and do it for this one. Notice it says find the exact value of all 6 trig functions using that figure, but we're missing our hypotenuse. So if you remember, the most important theorem in all of mathematics, of course, is the Pythagorean theorem, where the hypotenuse here we're going to call C. The side lengths are the legs of the right triangle. All right, we've got this right triangle here, 90-degree triangle. The legs are A and B, so we got A squared, so 12 squared plus 5 squared equals C squared, 144 plus 25. So step number 1, find the remaining side if it's not given. So C squared ends up being 169. And we're going to go ahead and square root both sides. Well, plus or minus 13, we know it's got to be the positive 13 because this is a side length. It's got to be positive. So C here is 13. That's step number 1. And then we can go through and find all 6 trig functions. Sine is opposite over hypotenuse. SOHCAHTOA, S-O-H. CAH, C-A-H, cosine's adjacent over hypotenuse. Tangent's opposite over adjacent. Oh heck, another hour of algebra. O-A, right? And then we'll do their reciprocals. So cosecant would just flip that over. Secant would flip over. The S goes with the C, C goes with the S, right? Secant goes with the cosine. Then we flip that one over. And cotangent, we'll flip that one over. So let's go ahead and do the first one there, sine of theta. Well, the opposite side of theta, here's theta right there. So the opposite side would be right there. That'd be the 5. That'd be the opposite side. The hypotenuse, of course, is always opposite the 90-degree angle, which means the adjacent side is the leg right next to the angle. Right, there's the adjacent side. So let's do sine of theta here. So sine of theta would be opposite 5 over hypotenuse 13. Cosine of theta would be the adjacent. That'd be the 12 over the 13. Tangent would be the opposite over the adjacent, so 5 over 12. There's 3 of our answers. Now let's just flip them over for cosecant. Would be 13/5. I'd flip that over. Secant would flip over the cosine. 12 over, oops, that was 13, sorry. So 13 over 12. And then the cotangent would, instead of 5 over 12, would be 12 over 5. And there's our all 6. This next problem, I'm going to actually make this a you try it problem. So this is a good time. Go ahead and pause the video if you're watching the video and try this problem first before it's worked out. So if you use that Pythagorean theorem, you get this square root of 33 there, right? So there's our B. Then at this point, now I got all 3 values, so we can go ahead and find SOHCAHTOA here, right? So our sine would be the opposite side. Again, here's the opposite side. This would be our hypotenuse, and this one here would be the adjacent side. SOHCAHTOA. So here our sine ends up being square root of 33 over the hypotenuse 7. Our cosine is the adjacent side, so 4 over the 7. And the tangent ends up being the square root of 33 opposite over adjacent 4. And then the reciprocal of the sine is the cosecant. So cosecant would be, instead of square root of 33 over 7, it'd be 7 over square root of 33. But we got to rationalize that. So you got to multiply top and bottom by the square root of 33. Let's see, I'm running out of room here. So the cosecant ends up being 7 root 33 over 33. Now let's do the reciprocal, the cosine, so the secant. So instead of 4/7, that'll just be 7/4. Let's do the reciprocal of the tangent. So the cotangent, flip that around, so 4 over root 33. Again, we got to rationalize that. So 4 root 33 over 33, there's our cotangent. Well, if you remember from last time, we had, like, for the 30, 60, 90 triangles, for our special right triangles, right, the 30, 60, 90, you could find, and then our 45, 45, 90. You can use that, and you could create a table of trig values for the 30, 45, and 60, right? Which also obviously correlate to the, unit circle, right? As well in quadrant 1. But let's go ahead and find the exact value without using a calculator. So we'll do it a couple ways. We'll do it with a special right triangle, and we'll also do it with the unit circle. So we got cosine of 30 degrees squared. Let's do it with the special right triangles first. So here's our 30, 60, 90 triangle. And notice the cosine of 30, so cosine of 30 is adjacent over hypotenuse, right? So this is root 3 over 2. Minus the sine of 30 degrees is opposite over hypotenuse. Right? Now, if I'm looking on my unit circle, and I had my cosine, I find my cosine of 30 degrees, right? I rotate 30 degrees right to there. The cosine is the x value. There's the root 3 over 2. And there's our sine of 30 degrees, 1/2, the y value there, right? So either of those would obviously work. Now let's finish the problem, because notice it had cosine squared 30 degrees. In other words, cosine of 30 degrees squared, right? So we're going to square that. So root 3 times root 3 is root 9 or 3. 2 squared is 4. So I got 6/4 minus 1/2. In other words, 3 over 2 minus 1 over 2, which is just 2 over 2, which is 1. Right? Now let's go ahead and do 1 minus cosine of 60 degrees all over sine of 60 degrees. Let's go ahead and do it with a special right triangle first. Actually, I take that back. I'm going to do it with the unit circle first. So I'm looking on my unit circle. I rotate 60 degrees on my unit circle, and I find this point, which is 1/2 root 3 over 2. And I say, well, the cosine of 60 degrees is the x value. So I got 1 minus my x value, which is 1/2, right? All over my sine of 60 degrees. Sine of 60 degrees is the y value, root 3 over 2. Right? If I was doing it, let's do cosine of 60. So I'm looking here on my right triangle. If I'm doing it with the right triangle approach, cosine of 60, the adjacent side is right here, 1/2. See how that's adjacent over hypotenuse? Now let's do it for the sine of 60. Again, this is my reference angle right there, the 60 degrees. The opposite side's right here. Sine is opposite over hypotenuse, root 3 over 2. That's how you get the sine of 60 degrees with the special right triangles. All right, well, we got 1 minus a half, so I got 2 over 2 minus 1 over 2. This is all over root 3 over 2. So I got 1/2 all over root 3 over 2. Multiply by the reciprocal, keep, change, flip, if you will. So I got 2 over 2 root 3, so I got 1 over root 3, and we just need to rationalize that. So we got root 3 over 3. Now we've got some cofunction identities, and where do these come from? By the way, these should have little degrees on them. Sine of 9, that's degree, 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 degrees. So sine of 90 degrees minus theta. Let me look at the unit circle here for a second here. Let me pull this up, blow this up. Do you notice how these are repetitive? So like at 30 degrees, you see how that one and that one are they just are flipped around, right? So let me come back to here. So let's take this first one. Sine of theta is cosine of 90 degrees minus theta. So I said, let's let theta be 30 degrees. And let's use this. So supposedly 90 minus, remember our theta is 30 degrees here. I let theta be 30. The sine at 30 degrees is the same at the cosine of 60 degrees. Well, let's check the unit circle again. So go back to the unit circle. Sine at 30 degrees, right there. Is that the same? Go over to the 60 degrees as the cosine at 60 degrees, which is the x value. Yes, it is. So that's thus the cofunction identities, and mathematicians just went through and proved all these cofunction identities so that we can use them. So let's do it for this one. Let's go ahead and write an equivalent cosine expression for sine of 33. Well, I want sine to go into cosine, so I'm going to use this one right there. I want sine to become a cosine. So let's use this cofunction identity. Notice I have 33, and by the way, that's supposed to be a degree right there. 33 degrees. That's my theta. So 90 minus 33 degrees. So sine of 33 degrees is actually the same thing as 90 minus 30 as 57 degrees, right? So like if you pulled up Desmos.com, let's go ahead and check that. You'll see, pull up Desmos here. Desmos.com, go click on that scientific calculator. See how I'm in degrees? I don't want to be in radians. I want to be in degrees. Sine of 33.544. That's the same as the cosine of 57. See that? 0.544. 639 and so on. So you can see that they're equivalent. Now I gave you these cofunction identities in terms of the degree. You could do it in terms of radians. So here I have cosecant of pi thirds, right? Notice this is in radians. I want it in an equivalent secant. I want cosecant as a secant. So I'm going to use this one. Cosecant of theta is secant of 90 degrees minus theta. Well, this, I don't want this in degrees. No, I want this in radians. So if you remember, 90 degrees is the same as pi halves, right? Right, I'll rotate 90 degrees, or if you're not sure, then change it to radians. 180 pi radians over 180 degrees, and you see how you get pi halves. So pi halves is the same thing as 90 degrees. So I'm going to use this. So cosecant theta is the secant of 90 degrees, or pi halves minus theta. I have cosecant, my theta here is pi thirds. So I have pi halves minus pi thirds. I got to go ahead and get a common denominator here. So times 3 times 2. So it looks like I have 3 pi 6 minus 2 pi 6. So the cosecant of pi thirds is the same as secant. I got 3 pi minus 2 pi all over 6. 3 pi minus 2 pi is a 1 pi all over 6. So there it is. Cosecant of pi thirds is the same as the secant of pi sixths. All right, let's keep going here. We'll solve this triangle. Notice when they say solve, that just means find the remaining angles and any side lengths is what they're asking you to do, but they're inferring, right, instead of explicitly stating that. Number one, notice all the interior angles of a triangle add up to 180 degrees, right? The three interior angles. So angle A, that's this one right there. We don't know that. Plus the 35 degree plus the 90 degree, all those add up to 180 degrees, right? So I got angle A plus 125 degrees equals 180 degrees. Subtract 125 degrees from both sides, and it looks like I end up with 55 degrees. So let me write that in right here. I got 55 degrees right there. All right, so we've solved for the remaining side. Now we need to find the side lengths, okay? Let's go ahead and call, let's call the hypotenuse x here. We'll call that height there y. How about that? Let's solve for x. So notice I have 35. Let me use 35 degrees. Let me use this as my reference angle. So I have the 200, and I want to solve x. So I have an opposite side and a hypotenuse, at least when this is our reference angle up there. So I'm going to use the sine because I know the sine is opposite over hypotenuse. So I'm going to use the sine. So I know that's opposite over hypotenuse. And my opposite here is 200. My hypotenuse here I called x. And now I'm trying to solve for x. So let's get our x on top. So I'm going to multiply x on times this side, x times that side. Now remember, sine of 35 degrees, this is just a number, right? I can punch that into my calculator, sine of 35 degrees. So I just got to get rid of that number. So let's divide both sides out. And so I just punch this in. Let's punch in 200 divided by the sine of 35 degrees. And let's see what that gives us. Make sure you're in degrees. I do. I check it. DEG is showing because I want this in degrees. I have a degree here. 200 divided by sine 35. 348.689. Write that. Move this back over. Feet. Of course, this is in feet. Okay, so there's that side. Now let's do the other side, the y value. Well, if I use the same 35 degree, then I could go adjacent. I want the adjacent side. I already have the opposite side. Who's opposite over adjacent? Hopefully you say tangent's opposite over adjacent. So again, opposite's 200. That's the 200. The adjacent side is what we don't know. And then multiply both sides by y. Divide both sides by the tangent of 35. And so let me punch this in. Pull up your decimal. Let's see. Okay, so 285.6296013. This is also in feet. Of course, you could round that if you need to round that. All right, here I've got a ladder is leaning against a building. Let's go ahead and draw this. Got this building. Here's the ground. Got this ladder leaning against it. Here's my ladder. It's leaning against the side of a building. And it forms an angle 72 degrees. So here's 72 degrees. It forms an angle 72 degrees with the ground. At the foot of the ladder, so right here, the foot of the ladder is 6 feet from the base. Here's the base right there, right? 6 feet from the base. So I'm 6 feet away from the base of the building. How far up So let's call this y. How far up, from here to here, right? The building does the ladder reach? In other words, and how long is the ladder? Let's call this x. How long is the ladder? We're answering two questions. We want to solve for y. How far does it reach up the building? And we want to solve for the ladder, right? So if I'm looking at this, hopefully you see the right triangle there, and you're thinking to yourself, what could I use? I want to only have one variable. Which trig function should I use? Should I use sine? Sine is 72 degrees, which would be opposite over hypotenuse. No, that's y over x. I got two variables. I don't want to use sine. Do I want to use cosine of 72? I could. That'd be adjacent over hypotenuse, but I kind of want to solve for y first. So how about we use tangent? That's the opposite over the adjacent. And then I can solve for the first question. How far up the building does it reach? I multiply both sides by 6 times 6 times 6. Y equals 6 times the tangent is 72 degrees. Let me punch that in. And this is in feet. So 18.47 feet if you're going to round that to 2 decimals. And then let's go ahead and do let's solve for x now, right? So notice I have the 72 degree. There's my reference angle. I'm going to go adjacent over hypotenuse this time. So I'm going to use cosine. Cosine is the adjacent over hypotenuse. So I'm going to multiply both sides by x. Remember, cosine 72 degrees is just a number, so I got to divide both sides by cosine 72 degrees. I'm going to go ahead and punch that in. So 19.42 feet is how tall this ladder is. When you look up at something, you have an angle of elevation. So if you ever hear angle of elevation, right, that's from the horizontal up, right? So that's an angle of elevation. Whereas if you see angle of depression, that's like you're on top of a cliff and you're looking down. So from the horizontal, the angle down, that right there in red is my angle of depression. Okay, so angle of elevation, angle of depression, two different things, but they're both off of the horizontal. So here's your first example. While standing 4,000 feet away from the base of the CN Tower in Toronto, okay, so here's this huge tower, okay, you're 4,000 feet away from the base of this tower, right? Here's the tower, and the angle of elevation is measured to be 24.4. We'll just imagine our eyesight is like right there at ground level for a minute, okay, because I didn't say anything else. So it's measured to be 24.4 degrees, this angle of elevation. Okay. Find the height of the tower. So let's go ahead and let this be x. And hopefully you're thinking to yourself, well, which trig function am I going to use? This is the opposite side. This one right next to it's the adjacent. Who is opposite over adjacent? Let's go ahead and use tangent. So tangent here, 24.4 degrees, is the opposite side, x, opposite over the adjacent side, 4,000. And then we'll just solve that. Multiply both sides by 4,000. Right, I'm multiplying those two. Pull up my decimals, 4,000. 4, looks like it punches in. So it looks like this is 1,814.48 feet tall is how tall this tower is in Toronto, according to this data. All right, let's do another one. An observer in a lighthouse is 66 feet from the surface of the water. So let's draw this. So let's imagine here's my water. I'm in this, like here's the lighthouse. Like I'm at the top of this lighthouse, okay? And it says this is 66 feet above the surface of the water. That's how tall this lighthouse is, 66 feet. I'm up here. At this point, I see a ship with an angle of depression. So, okay, so here's the horizontal. The angle of depression would be looking down. Okay, so this right there is 0.7 degrees. That's the angle of depression right there, 0.7 degrees. Okay. Estimate this, and this is the ship right here. There's the ship. Find the distance, right angle. Find the distance from the ship to the base of the lighthouse. We want to know that X right there. Well, if you remember from geometry, if you got two parallel lines, you got a line cutting through those. You have, if they're parallel lines, here, let me put the little, they're both parallel. You have alternate interior angles are equal. So if this is 0.7 degrees, then this is 0.7 degrees as well, right there. And so now I have a reference angle that I can use. And here's my opposite side. This one's my adjacent side. I'm going to pick the old tangent. So tangent 0.7 degrees is opposite over the adjacent. And multiply both sides by x, get the x on top. Divide both sides by tangent 0.7 degrees. Go ahead and punch that in. And get this. Feet. Now, notice it does say estimate the distance from the ship to the base of the lighthouse in miles. I did not do this in miles. I'm doing this in feet because my the height they gave me was in feet. So I'm still in feet. So let's go ahead and convert to miles now. So I've got 5401.904714 feet. Let's convert it to miles. So I know for every 1 mile, there are 5,280 feet, if you didn't know that. Feet cancel. This is over 1. So I got 5401.90474 divided by 5280. There it is in miles, 1.023 miles. All right, let's keep going with our bearings here. So bearings, this is a way to measure direction. So for example, north, 40 degrees east. Where's the angle? So think I'm looking north, and I'm going 40 degrees east off of that. So this is 40 degrees. That represents north 40 degrees east. Okay, that's the direction I'm going. So in other words, from point 0 where I started to point P, from 0 to P is north 40 degrees east. That's my bearing. That's just a way to measure direction. Let's do a north 65 degrees west this time. So off of the north, I'm going to rotate 65 degrees off of that, west, in the west direction. So this is my direction, north 65 degrees west. North 65 degrees west. Why don't you guys do this one? It's south. Well, actually, let's do this one together. I have a south one, then I'll give you another one. South 70 degrees east. That's south 70 degrees east. Last one. Why don't you guys, you try this one. Let's do south 80 degrees west. Here's our south. Off of the south, right, I'm rotating 80 degrees west. All right, let's keep going. A cyclist then rides for 10 miles. And then cyclist rides west. I'm sorry, cyclist. Let's go ahead and let's do it from the origin here. So here's our cyclist. It's going 10 miles west. 10 miles directly west. Right, to the left, right? 10 miles west. And then north, straight north off of that. So then straight north, 7 miles. And so, I don't want the arrow. Straight north ends up right there, 7 miles. Okay, what is the bearing from the starting point? Okay, so let me draw this right back. Let me draw the triangle. Okay, so the bearing back. So what we want is from here to there. What's the bearing? So north, such and such and such degrees, whatever that is, I'm going to call that theta. I want north, theta, in degrees west. That's what I want. Okay? So then you say, well, how do we do that? Well, let's go ahead and put, let me make this angle right here. How about alpha? Let me call that alpha. If I use that green alpha, can you see how I have opposite and adjacent? So tangent of alpha is opposite over adjacent, miles over miles. Notice they cancel. And so if I leave my angle, or I'm sorry, if I leave my calculator in degrees, and I go ahead and take the inverse of the tangent, this will undo it. And we will talk more about inverses later in the course. Right now, I just want to make sure you can use it and punch it into your calculator. So the arctangent of the tangent of alpha will just spit out alpha. So I just got to punch this in. So whatever the arctangent of 7/10 is in degrees, let's pull up decimals. That's how many degrees alpha is. Let's see, let's pull up decimals. Go to the function right there, FUNC, arctangent. Make sure you're in degrees. 7/10. Okay, so it looks like our alpha here is 34.992. We'll round that to 35. Let's go ahead and round that. Okay, so our alpha is approximately, we'll just use the approximate on this, 35 degrees. So here's 35 degrees. Well, notice this is a right angle itself, right? So number 2, how would you get alpha? Well, alpha plus theta adds up to 90 degrees, right? And we know alpha is 35 degrees. So subtract 35 from both sides, and we got 55 degrees. So finally, it's north 55 degrees west. That's the bearing back, right? It'd be north 55 degrees is how much you got to rotate. 55 degrees west, and that'll get you back the bearing from the starting point to the cyclist. All right, let's do one last one here. Jeep leaves its present location, travels along a bearing of north 58 degrees. Here, let's draw. We're starting in the middle here. Off of the north, we're going to go 58 degrees east. We're going to follow this for 31 miles. 31 miles we do this. 58 degrees right there, okay? So how far north and east, so exactly north and exactly east of the original position is it? In other words, how far east is it? Right, what's x? And how far directly north of the initial starting point is it? Right? That's what we're asking. Or how far north and how far east, same thing, right? So first thing I would do is I say, well, let's call this theta. I need theta. And notice I've got that 90-degree angle right there. So number one, theta plus 58 degrees does add up to 90 degrees. Let me subtract 58 degrees from both sides. And I've got 32 degrees. So this is 32 degrees in there. And so number two, see how I have the hypotenuse here? So I can solve, let's do y first. Here's the opposite side from y. So let's use the sine, opposite over hypotenuse. So the sine of 32 degrees is opposite over hypotenuse. And now let's go ahead and multiply both sides by 31. So it's about 16.43 miles. And this is like, again, this is how far north from the original position it is, right? That's how far north it is from the original position. Now, number three, let's go ahead and solve for y. Well, that's the adjacent side over the hypotenuse, so I'm going to use cosine. I'm going to multiply both sides by 31. Punch that in. Again, this is how far east it is. And then that's it for today's lecture. Appreciate you guys taking notes. See you next time.